Okay, in this virtual lecture, I want to finish up section 5.2 and then perhaps start and finish 5.3. We'll see how much I can get done. So just a reminder, I'm not going to be here on Monday. Actually currently in Iowa right now. I just finished giving my talk at a conference, so I won't be there, but someone should be there to cover my class. Don't know who yet, and um, all right, so let me share my screen. Okay, so hopefully you can see what I'm seeing. So let me get the book pulled up. So in 5.2, so this is, let me write this down. So 5.2, this is on trig functions on the unit circle. So, so we in in 5.1 we reviewed the unit circle. We looked at it. We found another way to view it. We were able to view it as a one-dimensional object. So in fact, here's just the unit circle right here. I have it already drawn, and and it's one-dimensional because if you imagine that your universe is just this circle and you live on it, you're an ant on this circle moving about. You can only say start at this point. This is our reference point right here. You can only move counterclockwise or clockwise. And so you only need one number, and this is going to be that parameter t, to specify a position on the circle. So that's what it means to be one dimensional. One dimension is roughly like how many parameters do you need to specify a position in that space. So for example, the plane is two-dimensional because you need an x coordinate and a y coordinate. And then yeah, so that's why the plane is a two-dimensional space. And so the circle lives in the plane. So it is, in a sense, a two-dimensional object. You have X and Y coordinates that specify a point on it. So, and they had to satisfy the equation X squared plus Y squared equals one. But it's also a one-dimensional object for the reason I just described, that if you measure distances in position relative to this point right here, 1, 0, you only need one parameter, and we call this parameter t. And then in 5.2, we defined the trig functions in terms using this picture of the unit circle as a one-dimensional object. So basically, if I give you a t value, so say given t is equal to here, let's say not say positive, but just um, given some t. Sorry, my computer's acting up right now. Given some number t, you'll start at this point, and this determines like an arc length, and you'll travel and then along the circle, and then maybe stop here. And this determines a point xy on the plane, on the circle, such that x squared plus y squared is equal to 1. Because that's what it means to be on the unit circle. A point xy is on the unit circle if and only if this equation is satisfied. Okay, and then the trig functions are basically like, so I give you, so let's say this length right here is t. So given this t value and these x and y coordinates corresponding to t, you define the trig functions as, like, say, for example, cosine of t would be the x coordinate, or cosine of y, sorry, cosine of sine of y would be the y coordinate, or tangent of t would be the y coordinate divided by the x coordinate. And then we looked at several examples. So now I want to determine whether or not these functions have symmetry. Because eventually we will want to plot these graphs. So this symmetry will help us plot these graphs, determine the whole graph, and also help with computation. So let's recall the two types of symmetry over here. So if I give you a function, just say it's from R to R, it's even if f of negative x, let's say f of t, because we're working with the variable t. F of negative t is equal to f of t. In other words, like the function absorbs the negative sign. It like can't tell the difference between positive and negative numbers. And it's odd if f of negative t is equal to negative f of t. And this is, of course, for t, real number. So what we want to do is determine whether or not any of the trig functions have these properties. All right, so given a t-value, let's say it determines this point right here on the unit circle. Well, if you travel, so now if this corresponds to traveling t, then negative t means you travel counterclockwise, right? And so maybe you travel here and then you land right here. But um and then this will determine a point on the plane on the circle, but notice this point right here. You can actually work out what the coordinates are in terms of this point right here, because this is just um a reflection. This point right here on the bottom is a reflection of this point on the top over the y-axis or the x-axis. So the point will be x negative y. So let me clean this picture up a little bit. All right, hold on. I'm going to pause this for a second. I think I have too many windows open. So let me stop sharing and then pause the recording for a moment. Hopefully this works now. All right, so I want to erase this here. So this distance right here corresponds to traveling negative t. So we have t means you go counterclockwise and negative t means you go clockwise. So let's evaluate sine of negative t and see whether or not we get this either one of these properties right here. Well, sine of negative t, remember, by definition, it's going to be the y coordinate associated point. So that's going to be this point right here, negative y. But now, y itself, right? Y itself, ignore the negative, is going to be sine of t or sine of positive t that without the negative, right? Because this point, the y coordinate here is by definition sine of t. So this is actually going to be equal to negative sine of t. So hence this shows sine is an even function. Okay. Because sine of negative t is equal to negative sine of t, and that's exactly this first property right here. All right, so what about cosine? Well, let's do cosine of negative t. Well, by definition, so we're gonna take cosine of t and it determines um this point right here. Well, cosine of negative t is gonna be by definition the x coordinate. So it's gonna be just x, but that's the same x here, and that's cosine of t. So says that this is cosine of t. So cosine of negative t is equal to cosine of t. So this shows hence cosine is odd. because it satisfies the second property right here. So sine is even, cosine's odd. And what about finally? What about the tangent of t? Sorry, negative t. We want to determine what that is. Well, by definition, that's remember that's the so again, negative t determines this point right here. So by definition, it's gonna be um the y coordinate over the x coordinate. The y coordinate is negative y, and the x coordinate is just x. So this is gonna be negative y over x, but I can take the negative and put it in the front, so it's gonna be negative y over x. Well, y over x is by definition tangent of t because when you take tangent of t, you take the y coordinate over the x coordinate. So this is negative tangent of t. So and then this shows hence tangent is odd. No, sorry, is yes, it's odd. Wait. Something's not right. Hold on. I feel like I did something wrong actually. Sine is the sine function. Wait, I get this backwards actually. Sorry, I did do it back. Okay, sine function is e odd. The cosine is even. So that means the tangent is odd. Okay. There's a table showing all the trig functions. We only did 3 of the 6 trig functions. So as I said, this is going to help us determine the graphs of these trig functions, but more immediately, it helps us with some calculations. So for example, let's do example 4. So we want to determine the sine of negative pi over 6. Now, because this is an uh, odd function, we can basically like factor out, in a sense, factor out the negative, pull the negative out, and write it like this. And now, I guess at this point you should draw a unit circle. I'm not going to draw it because, well, circles are hard to draw using OneNote. But you should, for your own practice, draw the unit circle so you can figure out what pi of 6 over it is. Remember, you need to evaluate sine, you need the y coordinate. So in this case, sine of pi over 6 is 1/2, so we're gonna have negative 1/2. All right, so the cosine, what about, so this is part A. Part B is we want to evaluate cosine of negative pi over 4. Well, the cosine is an even function, so it in a sense absorbs the negative. So this would be cosine of pi over 4. And this the x and y coordinates for this one are easy. Remember, they're equal. And in that case, it's root 2 over 2. So again, draw your unit circle. Whenever you solve these problems, draw your unit circle so you can get in the habit of remembering these values. All right, so um, here's some important identities. I'm not going to write them down. I'm just going to show you the book. So we have these important fundamental identities. Some of these we actually already knew right here. This first line we kind of I already pointed these out. Then we also have these ones. This one, first one's probably familiar. This is the Pythagorean identity, sine squared plus cosine squared is equal to 1. And then these ones might not be as familiar, but these two right here, these two, it's not picking it up. I don't know why. this one, and this one, they follow from this first one. In fact, let's just quickly look through the proof right here. So as I said, the reciprocal identities, the ones on the first line, these ones right here, they follow almost immediately from the definition. So it's nothing to do there. As for this other one, now no, so to prove the Pythagorean identities, note that for a given t right here, it determines a point on the circle, x comma y, and cosine of t is by definition the x coordinate, and sine of t is by definition the y coordinate. But x says since this point is on the unicircle, remember you're on the unicircle if and only if you satisfy this equation. But x, so x squared plus y squared equals 1, but x is cosine t and y is sine t. So just plug those in and you get this. So the Pythagorean theorem is, or yeah, the Pythagorean identity or theorem or whatever is pretty easy to prove once you have this when you define the when you define the trig functions in terms of the unit circle. It's pretty easy to prove. As for the other one, for the second one, just divide cosine t. Well, you got to assume that cosine t is non-zero. Um, just divide both sides by cosine t. So when you take this equation and divide both sides by cosine t, you get sine squared t over cosine squared t. Then you get cosine squared t over cosine squared t, but that's just going to be 1. And then you get 1 over cosine squared t. And then the squares right here, you can just kind of, oops, I don't know why I did that. You can factor out the exponent in a sense, and then factor out the exponent here. But then from these reciprocal identities, we know sine t over cosine t is tangent. So that's where we get the tangent squared. And then we know that 1 over cosine t, so 1 over cosine t is secant t. And that gives us the other identity, the second one. And then the third one is pretty much the same proof. Instead you divide by cosine t. So sorry, you divide by sine t so, to get that other identity. All right, I need to stop for a moment. Okay, so let's look at an example using some of these identities. So this is example number 5. If, let's say we're going to assume that cosine of t is equal to 3/5, and t, um, let's say corresponds to a point in the uh, say fourth quadrant. We want to find. I'm really tired, by the way, so I'm trying my best to get through this video. So bear with me. So we want to find all trig functions at this t value. So again, t is this parameter. I give you this t. You travel that many units around the circle. It determines a point x, y, and on the circle, and it's thought of as in the coordinate plane. And then we want to determine the other point, all the other trig functions at that. Well, the first thing we can do is get so if we know we know cosine of t is 3/5, and if we can figure out what sine of t is, then we actually can get all the rest of the trig functions for free pretty much, because all the other trig functions are defined in terms of sine and cosine. So once you know sine and cosine, you know all of the trig functions. Well, by the Pythagorean identity, we know that sine squared of t plus cosine squared of t is equal to 1. But we're assuming that this is 3/5, so we have sine squared of t plus 3/5 squared is equal to 1. And so this will be 9 over 25. And we can subtract that from 1. So we get sine squared t is equal to 1 minus 9 over 25. And when you combine these, you get 16 over 25. Now take the square root, and you get sine of t is equal to plus or minus square root of 16 over 25. But that's just going to be square root of 16 and square root of 25, so it's 4 over 6. Oh, sorry, 4 over 5. Oof. So now you might be like, you might wonder yourself, well, which one is it? Is it plus or minus? Well, since the point is in the fourth quadrant, sine of t needs to be negative, right? Because the sine gives you the y coordinate. And when you're the y coordinate. And when you're in the fourth quadrant, all the y coordinates are negative. So that means you're going to take when you're looking at these two roots, you're going to take the negative root. So that implies that sine of t is equal to 4/5. Sorry, negative 4/5. I just said that sine needs to be negative. And then, as I said, the rest of the trig functions can be worked out from there. So tan of t is going to be, remember, it's sine of t over cosine of t. So it's going to be negative 4/5 over 3/5. And so when you cancel those out, you get negative 4 over 3. And then cosecant t is going to be equal to 1 over sine t. So we got to just take the reciprocal of this number. So it's going to be negative 5 over 4. And then finally secant of t. That's going to be 1 over cosine t. So it's going to be 1 over 3/5 or 5/3. All right. I think that's all we need to do for that section. So let's move on to the next section. Now we're gonna look at graphs of sine and cosine. So this is 5.3. So 5.3. This is trigonometric graphs. So it's going to turn out that these graphs have, not only do they have symmetry, so you know you have either even or odd symmetry, they're actually also going to be periodic. So that means that the function in a sense repeats, and that's going to be manifested in the graph. The graph's going to repeat. So first of all, let me remind you what a periodic function is. So here's a definition. So let's just say you have f from, let's not specify the domain. Let's just say you have a function. So let's say let f be a function, and if so, of course it's on some subset of real numbers. Then f is said to be periodic if it repeats. That is like if you like evaluate it at one point, then some point further down along the real line, it should be have the exact same value. And that's how do you phrase that? Well, that it's you phrase it in the following way. You say that there exists a real number p, and this is called the period of the function, such that f of t plus p is equal to f of t for all t, let's say in the domain. I'll just use this notation domain of f. I didn't want to specify the domain, so it's just the domain of f. So this basically says if you want to calculate, so say you know f of t and you want to calculate the period at some point. Actually, it's not just any. Wait, back up. The period is not any. It's gonna actually not just be any number. It's gonna be some positive real number. So, like, say you want to calculate so suppose you know f of t and you want to calculate f of t plus p. Well, because this function has this period, that is, it repeats after every interval of length p, you can just calculate f of t and it's going to have the same exact value. So first of all, no, let's actually note this. This is an important observation. Periodic functions are not injective, right? So it's like kind of baked into the definition of periodic. Because remember, objective means that if you have two distinct points, they shouldn't you if you have two distinct points, then they're when you evaluate the function at them, they're going to be distinct. But t and t plus p are definitely distinct points. So t plus p is not equal to t, but this is saying that they have the same output when you plug them into this function. So this is periodic functions are definitely not injective. So they can't have an inverse. Um, so now, let's see. All right, so let's now verify. Here's a claim. Let's say let's I want to make a claim. Um, let's say how do I want to phrase this? Sine this is freezing. I don't know why. I feel like I said this already, but I'm really tired. Yes, I did, and then I told you to bear with me. So the claim is that sine and cosine have a period of 2 pi. And maybe you can already see this, right? So let's like kind of prove this. You can see why this is going to be true. So um if I give you, so what we want to do show is this, what does this claim amount to? So want to show that sine of t plus 2 pi is equal to just sine of t, right? That's what it means to have be periodic and have the period be 2 pi. And then cosine of t plus 2 pi is equal to cosine of t. And these are both, oops, I don't want to use that notation. I wish I could. I don't know why this is not responding. Oops, I don't know what I just clicked. This is for all. Oh my God, I've never had this much trouble using this. for all t. So we want to verify these. All right, and maybe you can, as I said, see why this is true already. So given t, you can say that this corresponds to a point x comma y on unit circle, right? So let's actually draw this. So let's see if I can quickly draw unit circle. We have this. We have this unit circle, and if I give you a t value, so you start here and you just kind of move along, and then maybe let's say you stop here. So this is you travel t, and you landed at x comma y. All right. Now, so and then so cosine. So this of course implies a cosine of t is equal to x, and sine of y, sine of t is equal to y. That's just by definition. Now travel t plus pi 2 pi units. All right, well, you can when you travel um distances, they're additive. So if you want to travel 2 feet, 2 meters, whatever, you can travel 1 meter and then another meter. You can break the you can break up the travel in a sense. So if you want to travel this many units, you can travel t units and then travel 2 pi units, or you can travel 2 pi units and then t units. So if you travel, um, so let's say you travel the 2 pi units first. Well, remember that's the circumference of this circle. So you travel all the way around the circle, and then land back here. But then if you travel, and then so you travel the 2 pi and landed back at the same spot because that's the circumference of the circle, and then you have to finally travel the t. So that means you travel here and then land here. So if you that means if you travel this whole distance, it corresponds to the same point, right? So that means if you so that means if you take cosine of t plus 2 pi, it's going to be equal to, well, the x coordinate, x. But that's equal to cosine of t. And if you travel sine t plus 2 pi, that's by definition the y coordinate associated to this t value, but that's y, and then that's also sine of t. So that kind of just finishes the proof. This shows that they're periodic with 2 pi. Hold on, I gotta stop this for a moment. All right, so at this point, I'm gonna pull up the book again because there's a ton of drawings and it's just not terribly easy to draw them through OneNote. So let me pull this book up. Oops. All right. So here's just that property I mentioned. This function has a period of 2 pi. And in fact, you can do even better. Um, the values of these functions actually repeat in this way too for any integer n. So so t plus 2n pi is equal to sine t for every n. And the same thing for cosine. So let's see. How do I want to explain this? Well, uh, not really sure what the hell they're doing here, honestly, with this table. So when you go from 0 to pi, Oh, I see what they're saying. Okay, so let's look at all the values between 0 and 2 pi. So let's like let t vary from 0 to 2 pi. So that corresponds to this first quadrant right here. So as t goes from 0 to 2 pi, you can kind of see what are all the possible y coordinates as you vary over that. Well, it's going to go from 0 to 1, right? When you vary from 0 to 2 pi, you start at the point 0, 1, 1, 0, and you kind of rotate around to the point 0, 1 at the top here. And you'll hit the y coordinate will basically be every number between 0 and 1. And it's increasing because as you get when you start here, as you get closer to the y-axis, your y coordinate's getting bigger and bigger, and it maxes out at 1, right? So this is the function. So when you plot the sine of t, it should be increasing, 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 max out at 1, and that corresponds to this point up here is 0, 1. Now, as now consider t values as you go from pi over 2 to pi. So you start at this top point right here, and as you go down towards pi, you can see that the y coordinates are decreasing. So that's where you max out here, and then you start decreasing until you hit 0, and that's when you hit the point pi, and that corresponds to negative 1, 0. And then now vary the t values from pi to 3 pi over 2. So you start at pi, which is right here. Hopefully you can see this cursor right here. Um, the y coordinate is 0. That's why it goes through the x-axis right here. The t-axis, I should say. It goes through the t-axis. And then as you start going towards 3 pi over 2, now the y coordinates are getting negative, and they're approaching negative 1. That's why we have this row here like this. So you cross the t-axis, and then you start to get towards negative 1, and then you hit negative 1, and that corresponds to 3 pi over 2. And then as you go from 3 pi over 2 to 2 pi, you're still negative, but you're approaching 0, because now once you hit the point 2 pi, the y coordinate is 0. So you're at this uh trough, this minimum, and then your y coordinates are getting closer to 0, and then they hit that. Now, this is all you need to know, because remember the sine and cosine have a period of 2 pi. So, and you know that the sine function is odd. So that means that you can figure out what the graph of sine looks like to the left of 0. It's going to be like a reflection or rotation, I should say. So here is sine repeated. So remember, the period is 2 pi. So the red portion is the portion we graphed above here, using this table and this picture of the circle to kind of figure out what those points are. And then it just repeats because it has a period of 2 pi. So it starts at 0, goes up to 1, goes back to 0, then goes to negative 1, and then it comes back up to 0. But then at that point, the pattern has to repeat. It has to go up towards 1, down towards 0, down towards negative 1, then up. And because it's odd, the graph has to look like it does to the left of negative 0. That's the only way the graph can look if the function is odd. All right, and then now let's take a look. So basically, you can go through all the exact same reasoning um, to figure out what cosine looks like. And in fact, they have this table up right here. They go through the same argument, like, okay, as t varies from 0 to 2 pi, what does cosine vary from? Well, when t is equal to 0, that corresponds to 0.10, so cosine is 1. That's why it starts at 1. And then as t varies from 0 to 2 pi, you start to climb up this, and your x coordinates are getting smaller. And in fact, they approach zero once you get to pi over two, because the x coordinate is zero there. So you can go through that exact same reasoning and get the graph um, cosine, which is right here. And again, it has a period of 2 pi. So at when t is zero, it's a maximum, and then it goes down, and then all the way down to -1, and that corresponds to pi, because that's when you travel pi units, when t is equal to pi, you start at this point right here, and then you go all the way around and land at this point. I really hope you can see what the cursor is pointing at, otherwise this is pointless. So that's the basic graph of sine and cosine. And just like with all the other functions we looked at, anything else is going to be a transformation. So we can take cosine and we can shift it up 2 units vertically. And then we can multiply cosine by negative, and that will reflect it over the y-axis. So here is f of x. So the graph in blue is the graph of cosine x. Then the graph of f is the one in red, because you got to shift it up 2 units. And then for part B, you have the graph of g is negative cosine, so that's the one in red, so it reflects over the x-axis. And so these are reflections or translations, but then you can also like vertically stretch right here by say 2, or you can shrink by 1/2. So here is a graph of those. So the graph in blue is just the original cosine curve, and when you multiply by 2, you get the red curve that stretches it. In other words, what this is actually going to be is you're going to be changing the amplitude of these waves. And then 1/2 shrinks it to get this, I guess, orange curve, or this tan curve or something like that. So that's that. And as I said here, so in general for these functions, you have these are stretches by a stretch or shrink depending on what a is. If a is bigger than 1, you're stretching. If a is less than 1, basically, you're shrinking. And the absolute value of a is called the amplitude. And it's going to be the largest value these functions obtain. So you can see when you multiply cosine by 3, it maxes out at 3. All right. Let's see. So find the amplitude. Okay, this is kind of a trivial example. Find the amplitude of this curve. Well, it's just absolute value of 3. So it's not much to do there. And there's the graph. Um, all right, so now when you multiply on the outside, say by a, that's going to have the effect of either vertically stretching or shrinking. But when you multiply by the x, when you do the multiplication inside the function by x, this, remember, has the effect of horizontally stretching or shrinking. Um, let's see. They kind of, this is a little tricky, this concept, but they explain it here, I think, in a pretty decent way. So you have the sine and cosine functions. They definitely have a period of 2 pi, the original functions. So what we want to know is what's the period of. So we know that sine x has period of 2, but we're not looking at sine of x. We're looking at sine of kx for some constant k. So we want to determine what is the period. Well, this is how they work this out. Well, they say to complete one period, that is for the graph to repeat, for example, as kx varies from 0 to 2 pi, that is k is between 0 and 2 pi, or so yeah, that means when you want to vary from 0 to 2 pi, you have to satisfy this inequality. But in this case, you can just divide by k. So what that means is that this inequality right here is equivalent to this. So what that in conclusion says is that these functions complete one period as x varies between 0 and 2 pi divided by k. So that means that the period is 2 pi divided by k. So these graphs, yeah, so these are the sine and cosine curves. And this is just a summary um, of just sort of this discussion. So these sine and cosine curves, they're in general this form. You can also translate them vertically or horizontally. And the amplitude is the absolute value A, and the period is 2 pi over k. So to figure out what the graph of these look like, you just graph the functions over the interval, this interval right here, 0 to 2 pi over k, because then that once you know what it looks like on that interval, it's just going to repeat. So here, let's look at an example. So they take y is equal to sine x2, then according to the above, and if you don't quite understand this, I encourage you to just read this on your own and think about it a little bit. It's good to read through the book on your own, along with, attending lectures. So we have this function 2x. So the fact that you're multiplying by the 2 is going to change the period. So what does it change it to? Well, you find that you take this value of 2 and divide it into 2 pi. So 2 pi divided by 2 is just pi. So it's going to repeat every pi units. So as it says, the graph completes one period in the interval from 0 to pi. And then for example, for this one, when you have 1/2 x, the period is 2 pi divided by 2, which is going to be 4 pi. So it's like you're stretching. So you're either just like compressing this wave or stretching the wave. See, like you're stretching this one, you're shrinking it. It repeats more often, in other words. And then you're shrinking it this way. Or sorry, I got it backwards. This is shrinking, this is stretching. So here are some examples. So the blue curve is the one and that's A sine X. So all these ones, we're looking at all the amplitude for all these examples right here is A. So they all max out at the same point. See? A, and then they have a minimum at negative A. But now when you have different K values like 2 at 2, 1/2, 1/3, you get these different graphs. They are getting stretched out in a sense. Or when you multiply it by 2, it shrinks it, compresses it. This is actually used to describe springs, for example, these functions. So here's just a basic example. I give you these sine and cosine curves, and you want to determine uh, the amplitude and the period. So for A, you just, you have 4 as the amplitude, so you just take the absolute value of 4 and you get 4. And the period, to get the period, you take 3 and divide it into 2 pi. And then for B, the amplitude is going to be the absolute value of 2, so that's just 2. That's what we're saying here. And then the period is going to be 2 pi divided by 1/2, like this, like so. And now you can also have functions of this form where you're going to subtract b from x. And that's going to have the effect of shifting it horizontally by this amount here, absolute value of b. So here's just a summary of that. So this is kind of just generalizing what we just did. So you have these curves, k is positive, some positive number. Then the amplitude is going to be absolute value of A. The period is 2 pi divided by K. And the horizontal shift is by B. And then to figure out what the graph looks like, you'll figure out what it looks like. You only need to graph one complete period. And for example, you can graph it on this interval. The interval from B to B plus 2 pi over K. So you take B and then you add the period to it. So here are some examples. All right, let's see what else is in this. Is there really that much more? This is getting kind of crazy, honestly. So I don't think this last part we're gonna really care about. No, I don't even care about that. That's crazy. Not terrible, but you can have a variable amplitude. So you can take a cosine function and multiply it by another cosine function, and you get some really crazy stuff. Oh yeah, this is important in calculus, as I said. You can take limits of this stuff. All right, let me go back up. I don't think there's really anything else we want to do. So let me just check one more time though. So we just did that. Fine. All right, I guess we'll just like quickly work through four. So you have this function right here. It's 3 times sine of 2 times x minus pi over 4. So amplitude is the absolute value of 3. It's just 3. And the period is going to be 2 pi divided by 2, which is going to be pi. And then notice it's minus pi over 4. So that means we're shifting. It's going to be horizontal shift to the right when you subtract pi over 4 units. So to to be able to figure out what this graph looks like, we only needed to graph it on this interval right here. This is b, pi over 4, and then this is b plus the period. So pi over 4 plus pi. And when you add those, when you simplify this, you get pi over 4, the interval from pi over 4 to 5 pi over 4. And here's a graph of it over that interval. So it's kind of like, well, yeah, you can see it's the cosine, so it maxes out at 3, so it's a vertical stretch. And then you multiply by 2, so you're compressing it a little bit, multiplying by 2 right here. And then you shift it over. So normally, like this part right here would start at 0, so you shift the whole thing over pi over 4 units. All right, that's all we're gonna do for today. So I guess what that means, um, we are gonna cover 5.3 and maybe 5.4 at some point. But whoever's gonna teach your class, I'll probably just tell them to start at 5.5. So we'll jump ahead a little bit. And then when we get back together, I'll go back to these two sections. And then hopefully soon we'll be in chapter 6. And we can finally get our second test exam in. All right, I gotta stop. I can't do anymore. So I'll close this out and then I'll upload it to YouTube as soon as I can.